Okay. Hello, my name is Garrett Fitzmaurice and I'm a professor in the Department of Biostatistics at the Harvard T.H School of Public Health. And joining me today are two of my close colleagues, Nan Laird and Jim Ware. Nan and Jim are both professors in the Department of Biostatistics. They're also pioneers in the development, the application, and really the translation of longitudinal methods to important scientific problems in public health and medicine. And I'd like to sort of really spend some time really looking back over some of your contributions, as well as hopefully we'll have some time for looking forward in a longitudinal sense. But before we even begin talking about some of your contributions, I was wondering if you could say a few words about your interest in statistics as a discipline. You both studied as either undergraduates or graduates. You chose to study statistics, and I'm curious about where that interest arose, and secondly, your decision after graduation to choose a career in biostatistics and the application of statistics to public health. So maybe Nan, you could start.
Sure. Well, I think as is typical of many people in statistics and biostatistics, in high school I loved math. I loved a lot of things, but math was easy for me. It was fun. And so I always kind of assumed I would major in math in college, which I did, but math in college was very different. It was hard. It wasn't fun. And so I left math and moved over to French, but that didn't really stick, and I dropped out of school for a couple of years, and when I went back, I decided I wanted to do something really practical, and I'd heard about computers. Computers in that era, it was like big mainframes at a few universities and punch cards. And
so now this was the early 70s?
This was, the very early 70s. Right. And so I thought, well, computer science would be really practical. I'll do computer science. But fortunately for me, I was at University of Georgia, and the computer science and the statistics department were the same. So I went to visit with the chair of the department, who was Carl Cossack, and he said to me, really statistics is much more interesting
than computer science.
Right. And he said, why don't you take this course I'm teaching? So I took his course, which really was not about statistics or computer science. It was elementary decision theory, taught out of the book by Herman Chernoff. And for me, that was so exciting. It was just a revelation that you could use mathematical formula to solve everyday practical personal problems even. So I was thrilled, and later on I realized that statistics is different from decision science, but nonetheless I was into statistics. And so after graduating and after I worked for a couple of years at MIT on inertial guidance systems, I actually I had a chance to go back to graduate school, and there wasn't any question about what I would go to statistics. I went to the statistics department at Harvard. And then when I graduated with my PhD, there was an opening here at the School of Public Health. And that, I think, was just fortuitous that I got into biostatistics. And it took a few years for me to figure out what I was doing here, but I was really happy to be at the school and happy to be in biostatistics. I will say, just sort of in prelude to what Jim will say, and my relationship with Jim is that when I first came, the department was very small, and they basically just taught courses for students in other departments. There was a very small graduate program. And so I spent a lot of my time teaching elementary biostatistics, and I didn't really have a project that I could dig my teeth into, and so I was kind of floating around when Jim Ware showed up, and I was so happy to have Jim Ware, first of all, as a colleague, because I was kind of lonely in the beginning. There wasn't really anyone like me in the department. And also Jim engaged me in some of the work that he was doing, and that was very interesting and exciting for me.
Well, thank you, Nan. You've really sort of brought us up to the intersection with Jim. And so, Jim, maybe you could just sort of just backtrack a little bit.
I have a story somewhat similar to Nan's. I was an undergraduate math major at Yale and did very well in coursework, but I never thought I never saw myself as a brilliant mathematician. In fact, my roommate had a faster computer than I did. You know, I mean, well, you know how it is in math. There's a gift, there's a creative part, and I just thought, I don't think I'm going to be able to hit a home run in mathematics. But anyway, I went on to graduate school in math, and fortunately, I went to Stanford, and I was in the math department and thinking, well, are these really the things I want to learn? Like a lot of engineering math and you know, all sorts of stuff, topography and things that didn't engage me very much. And then I went to a mixer one night, and Lincoln Moses showed up, and Lincoln was the founder of the statistics department at Stanford, and he talked to me, and I don't remember how he arrived at this, and he said, you should really come over and take courses in the stat department. So I started doing that. I took Manny Parsons' course on stochastic processes, for example, and I said, yeah. And so after 1 year, I switched to the stat department. And then turns out the stat department at Stanford has a very close relationship with the medical school. So almost from the beginning, I sat in on courses where med school professors in the med school would come and present some problem, and then the professor would assign it to the student. Help this professor do this. And so I got an exposure to biostatistics. So then when it came time to look for a job, NIH was a natural place to look, and that's where I went. And so that's how I kind of naturally followed my interests from math to statistics to biostatistics.
That's interesting. So the two of you, so you moved to the Department of Biostatistics in was it the late 70s?
Here at Harvard, you mean?
Yeah.
I came in 79.
In 79. So the two of you, did you immediately start to interact in terms of collaborations? Because as we'll talk about, you know, one of your most pioneering papers was the biometrics paper in 1982. And what I'm sort of curious about is what happened before the development of that paper. So,
well, I'd like to say one thing about that, and then Nan, I'd like to hear. I'm fuzzy about how you and I struck up the partnership. I don't remember the details of how that began, but I came here with a lot of interest in longitudinal data because when I was at NIH, we had a lot of longitudinal data, and we were using primitive methods, the so-called two-stage method, which is called the NIH method. And Manning Feinlieb, who was head of EPI there, kept asking me, how can we use measurements of children to understand what happens in adult life? Think questions like life course questions. And so Margaret Wu and I wrote several papers trying to do prediction of future outcomes and so on. They were simple in retrospect. Excuse me. But they were part of an interest in longitudinal data. And then when I came to when I came to Harvard rather, I had the very good fortune to be asked to join the Six Cities group and immediately confronted a host of longitudinal data problems, and I'm sure that I came and talked to Nan about them, but I don't remember those early conversations.
So it was really your involvement in Six City studies when you came to the School of Public Health, which is one of the most prominent longitudinal studies that's had a huge impact on both public health and policy. That was really the source of your interest in some of the methodological challenges.
Yes, I mean, I had a kind of an intrinsic interest in longitudinal questions. I thought they were interesting, and you see how important life course research is now. And so I think that was a good instinct. But then when I came to Harvard, all of a sudden, I had a big responsibility. We had to deliver insights about how exposure to air pollutants affects growth of the lung, decline of the lung during adult life, respiratory symptoms, all those sorts of things. So we had to really produce the results that drove that study.
In preparing for this interview, I reread your biometrics paper, and I was struck by two things. One is the examples you used were from the six-city study, and so I suspected that was the initial impetus for the work. But the other thing that's very striking about the paper is it's not a paper that just solves one problem for one data set, which is very, quite typical of a lot of methodological work. A single scientific issue in a particular data set requires an adjustment, an extension, but the paper had really great generality. And so I was wondering if you could tell us a little bit really about how the paper evolved. It may have evolved from discussions around some challenges with Six Cities data.
So Nan, I'd like you to take the lead on that, but I would like to say it happened pretty quickly.
Yes, it did.
I arrived in 79, and the paper was already published in 82, which meant we had to finish it by, say, 81.
Well, I was just going to add, in reviewing the paper, I did look at the end of biometrics paper where they still reported when a paper was submitted. It was submitted in April of 81. So that's why I'm sort of curious about how quickly the two of you partnered up.
Arrived. That's amazing, isn't it?
Yeah.
So my memory was that you asked me specifically about the work that I had done with Don Rubin and Art Dempster on the EM algorithm. Because, the EM algorithm itself is a pretty general way of framing a whole host of seemingly different problems and offering a kind of computational method that unifies them. So I think, Jim, my memory of it is that, so partly Jim and I just became friends. I think we were kindred spirits, but I also remember specifically Jim struggling with this issue of how to deal with the six city study data, and thinking that the work that we had done on the EM algorithm would really be relevant to this problem.
I was so blessed that Nan had such insight into the methods that were directly relevant to how our work evolved. Not only that remarkable EM algorithm paper, but also your dissertation.
My dissertation.
About mixed models for categorical data, really.
Yes, and random effects and empirical Bayes. All of those were things that I was really interested in.
They had all these insights that were the keys.
Right, right. But what's really quite amazing about the paper is it goes a little bit beyond just solving the particular problems in the Six Cities data that you used in the examples. And so I'm wondering, at some point did the paper evolve into, did you recognize really the generality of the paper that you were writing and its potential impact that it was going to have?
So my experience, not so much with that paper, although to a certain extent, is that very frequently you don't realize the generality of what you're doing. It's other people who suddenly look at the paper and say, well, this works for that and that and that. But as we were saying earlier, I think one of the things that made the paper so popular was partly the fact that it was so very general, but it was also very familiar because we framed it all in terms of kind of simple, ordinary linear regression problems, which I think really is what made it attractive to people.
So that aspect really resonated with researchers. So as you've put the final touches to the paper, did you have a sense of its importance?
No, I think as Nan says, we were focused on solving a problem, and I didn't appreciate how generalizable the results were. But I did know that it was a big step forward because really methods, as I've hinted at before, the methods for analysis of longitudinal data were very primitive. They were based in multivariate models with missing data and that sort of stuff, and they were just not models that you could use intuitively to solve problems. And so there was a real impasse there, and we did get over that impasse with that paper for the linear, for the measured outcome.
Right. Fairly soon after publication of the paper, it became known as the Laird-Ware model. It was a term that I heard very often as a student when I joined the department. I never heard that term from either of the two of you, though. I don't think you ever used that term in many subsequent publications that you wrote in your teaching and courses I attended and gave jointly with you. And I think I've always suspected part of the reason you've never used that term is your inherent modesty, and you're two of the most understated people that I know in terms of the incredible achievements you've both had in your careers. But I also wondered whether it was in part because you also wanted to sort of give due recognition to some of the earlier work that influenced your paper. So there was, you talk about the state of the art at the time you were writing the paper as being quite primitive, but there had been work on growth modeling, which again wouldn't quite solve all of the problems, but it laid some of the foundations for the ideas. And there'd been work on random effects models by Harvard and so on. And so I was wondering, could you sort of put the paper in some sort of context from the sort of the sources that you drew on?
So I agree with you that the sort of classical methods for growth curves were, well, for longitudinal data were in the growth curve literature, which were all classical multivariate. And so there was a whole sequence of textbooks on classical multivariate problems, and they never talked about anything like lack of balance in the design, lack of normality, lack of linearity, or missing data. These just weren't discovered or discussed.
Right.
So it was very hard, but there were beginning to be a background on variance components that allowed you to fit much more flexible models. There was also Jenrick and Schluchter, as well as Harville's work. And then there was also work on iteratively reweighted least squares and generalized linear models. And I'm not sure when that work was done, but I think it was
Aiken had a paper.
Yes,
and then a paper that influenced me was Rao's paper on growth curve models, which I think also was in biometrics, but again, didn't deal with incomplete data.
Right.
But he did, I think, address empirical Bayes, which is
right.
And the sort of family of models was related to ours.
Right.
But you're right, Garrett. I never referred to the work as the paper as, or the method as Laird and Ware, except I did discover at some point when I was teaching here at the school, it was such a ubiquitous term that whenever I talked about the linear mixed model, I felt I should explain to the students that some people called it this. So I would say to the class, well, some people call this model the Laird and Ware model, but I would never call it that myself. And they always get a kick out of that.
Right. So, I mean, from my perspective, I think, one of the really important contributions of the paper was its generality. It really, all of the methods that preceded it, the growth models, they were all special cases, but you actually sort of presented a regression framework that allowed much greater generality, that could handle all of the typical imbalance and mistiming of measurement, that could handle both time varying covariates as well as time invariant. And so it was just this very, very general framework. And that's what I was sort of mentioning earlier, was the intent to write a paper that could handle so many different types of problems.
Well, no, I think that there was that intent. I feel there was definitely that intent, although the extent to which you're successful is not something that you can really judge at the time, but you get judged later.
And I had said before that when I see the development of biostatistics in biomedical research, especially clinical research, I see it as it's really all grounded in the linear model. That when you think about the proportional hazards regression model, logistic regression, which of course preceded it by a couple of decades, and then our work, it all can be understood from a linear regression perspective. And I think that that is the point of departure for non-biostatisticians trying to use more advanced methods. And I think it's when people relate a more sophisticated method to a more familiar and simple method that they can adapt it even though they don't understand all of the machinery in the back room. They have an intuitive understanding of how to interpret the results of the model. And that, I think, was a very important feature. Nan has mentioned that we used linear regression notation. And so we made that link explicitly.
Right. So I think that certainly probably had helped a lot with the translation of your work to many different areas. And I'd like to actually return to that theme of, I think it has an important ramification for teaching and education. And so maybe we can talk about that a little bit later, about the way in which we actually develop and teach courses about regression. Another aspect of your 82 biometrics paper I was curious about, because it proposed and relied for estimation and inference on the EM algorithm, which was computationally quite demanding. This was the 80s. This was the era of really the availability of
I think I had my
tremendous
first
advances in
desktop computer in
Yeah.
82.
Yeah. But this was also the era where there wasn't open source statistical software like OR. There was always a sort of a reliance on methods being picked up and adopted by often commercially available software before they really would move into the mainstream. And so I'm sort of curious about, was there a lag in terms of the implementation of the methods you described in your paper, how long that took, and whether that, was that lag sort of an impediment to really its more widespread use?
Well, Nan, you remember there was a lag. I mean, there was that period in the 80s where both the UCLA group and the SAS group were trying to develop those methods and were interested in them, but it was a slow process. And I don't recall, there was somebody at SAS who was pretty sophisticated.
Yeah, that was Russ Wolfinger.
Right.
Yeah.
And so he was instrumental in identifying some computational issues and in incorporating mixed models into the SAS software. I couldn't say exactly, but I would guess it was 6 to 8 years after our paper that people had ready access through SAS to those methods.
I was doing a quick search on that, and I believe that the first implementation of proc mixed in SAS wasn't until 91, 92.
Okay, so it was a decade.
Which tells, I think our students today will be quite shocked that there could be a 10-year lag between important developments in the statistical literature and when they're readily available.
So let's not forget Nancy Cook, who was a student of Jim's at the time. One of the things that she did in connection with her thesis was to write a program, I think in Fortran, for doing the computations. And I can remember that being pretty widely distributed for several years. It was pretty popular.
And you and I taught some short courses.
Yeah.
And I remember Scott and Kung Yi came to one of our short courses and were, bright as beavers and all excited. And, this is great. What do you think about this and that? And they were full of ideas about what they might do. And I think at that time people would take our software.
But so Garrett, I'm going to take issue with you on something. You keep talking about how what was your word about the EM algorithm as a computational?
Computationally demanding.
It's computation. So what do you see as a easier computational method for the linear mixed model?
No, it wasn't really it wasn't a criticism of it, but it was just
that
that
it required
although
work.
computing was really having a powerful impact on statistics, if this wasn't the times where there was open source statistical software where important publications were very quickly or even simultaneously complemented with a program to implement the methodology. And so I was just curious about why there was such a delay or a lag before the methodology was adopted.
That was common.
I think it probably was for all methods.
I actually remember the SAS softwares being available pretty fast. I felt that Russ was working with someone, maybe Jenrick and Schluchter, or maybe Harville, but Russ was really pretty far ahead of his time, I think. He was pretty quick.
He was very thoughtful.
Yeah.
Right. And I think you mentioned the group in California. Was that BMDP?
Right.
Yes.
And I seem to remember they may have sort of beat them to it.
They did
they had a sort of a module.
That's right.
Yeah.
Although I never learned how to use it.
Yeah.
As we've sort of discussed, the linear mixed effects model really has had a very enduring impact on longitudinal analysis. It's become almost a sort of a default method for the analysis of continuous outcomes. As was the case in many developments in statistics, extensions of the mixed model methodology to discrete data took longer and had many more challenges. One of the important papers you wrote on that topic was a paper with Robert Stiratelli that was published also in Biometrics in 1984. And before we talk about that paper, again, I'd be interested to hear a little bit about what the landscape was like before you wrote that paper. So this was a paper, interesting, I reread that paper and also looked to see when you submitted it. And this was a paper you submitted in January 1982, very soon after publication of Laird-Ware and Biometrics. And so I was wondering, in the late 70s, the early years of 1980s, what were the sorts of methods people were using to analyze repeated binary data? Was it again an issue that you were working on scientific problems? Were the existing methods just, weren't up to the challenge?
I mean, there was a lot of work on Markov models and modeling transitions, but it wasn't. None of the papers. Bert Singer did some work on that topic, and some of my colleagues at Stanford did a lot of work on Markov modeling, but the models weren't framed in a way that you could apply them to the kinds of problems we were trying to solve. So in the Six Cities study, we wanted to know whether exposure to cigarette smoking in the home causes a child to have respiratory illness. So it's another kind of regression problem, or it could be framed that way, but none of the literature seemed appropriate. So there was a gap there. And so naturally, having repeated measures of these outcomes, I mean, you could have done logistic regression or something, but having repeated measures of these binary outcomes, it was natural to say, well, is there an analog to what we've done for the measured outcomes?
Yeah. Sorry, Nan.
Yeah, I would just add to that was Grizzle, Starmer, and Cook had a method.
Yes, he did.
Which was extremely general, actually. But the drawbacks were it was very limited in the type of between subject covariates that you could have.
You were restricted to categorical, essentially.
Yes, it was for categorical. data
kind of a
entirely.
contingency table approach.
Right.
And the other thing, quite frankly, again, I hate to harp too much on notation, but as I recall, their notation was so complicated. It took a long time to sort of get past the notation and figure out how general the work really was and what they were doing.
Yeah, I think that methodology, had many of the limitations which you really tried to address in your linear mixed effects model paper, which was, not being restricted to just grouping variables, but being able to have quantitative, both time varying and time stationary covariates and confounders you want to adjust for, and all of the complications. And that methodology just was limited in that respect. One of the challenges, though, of applying the random effects in the case of logistic regression models, your paper focused on repeated binary data, was the intractable likelihoods that, the requirement of it, the marginal likelihood required integration over the distribution of the random effects, and that didn't have a closed form and was quite intractable. And you posed really a very sort of interesting approximate approach to handle that problem, essentially relying on a Laplace approximation. And so can you give us a little bit of sort of context for that paper?
Well, so I think, Nan, you suggested the method that Garrett is referring to, and we were able to implement that, but in the setting with relatively few observations per subject, we subsequently learned that it wasn't as robust or as stable as you would like. I mean, that there was a lot of uncertainty around estimation at the individual level. As you know, there are two general approaches to these categorical data problems. You can either try to estimate population level quantities, what proportion of the subjects exposed to X have the condition Y, or you can try to do a subject specific, how does this exposure affect this individual? And our model was a subject specific model, which meant you had relatively few observations in our setting, maybe 6 or so, to estimate those subject level parameters. And subsequent work showed that it wasn't as stable as one would like it to be.
Right. So part of the problem was you had really too little information about the variance component in that setting with just a few repeated measures. You already sort of alluded to work that came soon after the publication of your paper. I mean, I think your paper actually had a huge influence on the field. It was initially focused on the analysis of repeated binary data, but I think many other statisticians were quick to jump on recognizing the generality of the approach, the generality of using approximate methods, and it really laid the foundation for decades of research on what became known as penalized quasi-likelihood, and Norm Breslow and David Clayton wrote a really nice paper that I think was very influential. So the paper really, I think part of its contribution was that it really led the way, a direction for further research for many other statisticians, and it really has become a sort of a very important area. Soon after publication of that paper, your colleagues in Johns Hopkins, Kyung-Yi Liang and Scott Ziegler, they also published companion papers in Biometrics and Biometrica on generalized estimating equations, which also became a sort of a game changer for the analysis. Although they presented in the context of both longitudinal and correlated clustered data, I think it really had a very important impact on longitudinal data analysis. You subsequently both have done methodological work, applications that have used that methodology. And so I was wondering if you would maybe want to say a few words about some of the differences between the approaches and their relative importance for addressing the sorts of questions that you were confronted with in public health and medicine. Because as Jim already alluded to, there's really these two different strands of approaches, population averaged approaches or marginal models versus subject-specific or conditional models.
So, of course, for the linear model, the two approaches coalesce or really are closely linked, and so there's not a tension. And so it really, that was, in a way, their paper in some ways generalized or created a larger context in which to think about the random effects models that we had advocated. But in the categorical case, there's a real difference. And my experience has been that in population research, like the six-city study, what you're interested in is the marginal effects. Yeah, very often, you're not. It's interesting now with this great interest in personalized medicine that people, I'm sure, will try to think more about individual level of relationships. But for a lot of research that I've been involved in, it seems more natural to try to estimate marginal effects. What's the population impact of this exposure? And so that's the setting where you do turn to the generalized estimating equation approach and the modeling that they've described. And that was, to me, a huge paper that just really had a big impact on my applied work.
Right. Nan?
So first of all, I agree with you. It was a huge paper. But, thinking about it, much of what they did was just borrow our notation for modeling the mean response and free us up from our obsessive worry about modeling the variance-covariance structure. I mean, I think they were the first people that said, well, let's not pay much attention to that. But if you haven't used a model for that, then you have to be concerned about how to fix up the variance. But I agree completely that I would tend to suggest that approach for binary responses. On the other hand, I don't really agree with what you said about the linear model and why I would take the linear mixed model approach over the GEE approach. The main reason is that GEE is not really satisfactory if there's a lot of missingness that is not simply missing completely at random. It's not really a satisfactory approach. And it doesn't make as much use of the information that you have in the data that you could. So I always prefer to use a linear mixed model for the for the repeated measures. And I have to say, I think some people get confused about the term linear mixed models, and they don't, for example, realize that a spline is a linear mixed model, and they think somehow a spline doesn't fit into that framework. But it does, and I think it's more flexible because of the fact that it utilizes more information about the data.
Yeah. I'm glad you mentioned splines and mixed effects models now, because of the third paper that I wanted to highlight. It's a paper that, a Jasa paper in 1995, was work that you both did with Crystal Donnelly. And it was really, I think, a very important paper because it put smoothing within the context of linear mixed effects models. And I think the particular application you were interested in there was getting smooth individual specific curves. And again, I think it was a problem from the Six Cities data set. I know many years ago I visited Matt Wand in Sydney, and when Matt came to the School of Public Health, he was somebody whose entire research focus was on smoothing, but taking a very more traditional statistical approach to smoothing. But when he arrived here at the School of Public Health, he told me that he was very influenced by your paper, and in fact a lot of his work that he did in terms of applications while he was here at the school was really exploiting the connections between smoothing and mixed effects models. So I think it's a terrific paper, and it's one that's really had an impact. It hasn't just shown the versatility of linear mixed effects models, which you're referring to, but I think it's really helped to sort of move smoothing into sort of the mainstream, because I think many empirical researchers and quantitative scientists just can see the connections a little bit easier when it's something familiar. So that's a really wonderful paper, and I was wondering if you could give me some context for that paper.
Well, that's such an attractive modeling strategy for a lot of important questions. As you said, understanding individual trajectories and so on. I always feel like I could have done more on that topic. I mean, we had Crystal's paper, and then I had a student, Miriam, I can't remember Miriam's last name now, who did a similar paper, which was published in Statistica Sinica, which was, again, trying to incorporate smoothing. But I think that I wish now that I had pushed harder on that, because that's I think a really useful extension of the basic linear mixed model,
right.
And quite interesting, related to some of the work Grace Waba did and
right.
others have done, trying to understand various ways to fit individual trajectories. Yeah.
So what I remember about that paper was that Crystal actually got engaged with you on, again, well, it maybe wasn't 6 cities study, but it was a related study of air pollution, and measurements were made at schools, and the idea was how to actually obtain better estimates of the true exposure of children when you had a limited number of spatial monitors. And I remember that Crystal had gone through a lot of the literature on the so-called kriging, which was very popular at the time, and she'd sort of figured out that could be related to this model. It was for me, it was a very eye-opening paper, the extent to which it could be generalized. With other
connections back to the linear mixed model.
Well, and you bring up the fact that the 6-city study was a tremendous source of all sorts of methodologic challenges. Nan's now mentioning the exposure side, which had all sorts of complexity and issues. And so we were just so blessed, I feel like, to have that opportunity to arrive and simultaneously be invited to join that wonderful study, and then to be able to have a colleague like Nan, who was such a powerful contributor to the work and drove so much of the methods. It was just such a blessing.
Well, it sounds like it was sort of really the perfect blend of really scientific problems driving the methodology and not the other way around. But nonetheless, the papers that you wrote have really been pioneering in terms of pointing out solutions to much general problems than the original ones that you described in your papers. What I'd like to sort of talk about is something that I remember well, because I was a student in the department in the early 90s, was that there was also a tremendous amount of excitement and buzz around the department in terms of the amount of work that was going on within the department in longitudinal analysis. This was also the time of CBAR, or an SDAC, as it was previously known there. It was the major AIDS clinical trials network, and they were generating lots of problems in longitudinal clinical trials. And so I remember it just as being a very exciting time. It was a period that came soon after many of your pioneering papers, the papers by Kyung-Hee Liang and Scott Ziegler. There was a lot of student work going on. There was a lot of postdocs. There was a really exciting working group in longitudinal analysis that was very well attended. And so I was wondering if you could sort of maybe just sort of talk a little bit about that. I mean, I saw it as really sort of the perfect laboratory for longitudinal research, and I suspect a lot of postdocs and visitors came to the department for that reason.
Yes, I thought it was a very exciting time. We were both working with lots of students who were working in this area, and there were postdocs who were, I remember Dan Stram came and did quite a few papers with us as a postdoc, and I remember Kyung-Hee Liang came and visited for a while, and that was before their GEE paper, and I can remember reading a preprint of that paper and commenting on it with him. And it was a very exciting time. There was a working group where students would present their work in progress, and there was a lot of, it was also a period I felt where, you know, the classical clinical trial model in cancer was you followed people for survival. But in these chronic diseases that people started to look at, AIDS being one, you would have a repeated measure, say perhaps the CD4 count, or for children it might have been some psychological measure of development. So there were beginning to be a lot of what I would call longitudinal clinical trials, and these clinical trials had a lot of issues with dropout and non-response, and that sort of led to further work and development on these kinds of problems. I remember one student, Joe Hogan, who worked quite a lot on this, and it sort of moved us into a slightly different area of application. And then we also moved into different kind of models, like I'm thinking of Nick Horton, who worked on multivariate responses as sort of a different kind, with you and myself.
Right.
So it was a very, very exciting time to be at Harvard.
And then there was the complementary set of problems of missing data, which were so common in longitudinal studies, and there was tremendous amount of research going on in the department on missing data problems. And so I remember it as just a tremendously exciting time. You just felt that you were in a department at the cutting edge. And
one of my aspirations for the working group was that we would write a book. I was inspired by Fred Mosteller's working groups when I first came to Harvard. They had a working group related to the New England Journal that wrote a book called Medical Uses of Statistics, which I thought was very interesting and very practical. And I had the idea that we might be able to do that with our working group, but we weren't able to really accomplish it. Even though we wrote some drafts of chapters and things, we weren't able to accomplish it. And it wasn't, Garrett, until you had the inspiration to work with us on the textbook that we finally got that project off the ground. I'm so proud to have been associated with that work, and I think you were instrumental in making that happen. That Nan and I don't know why exactly, but it didn't come together to produce a book when we were working with the working group.
Yeah, I suspect it might have had something to do doing Dean of Academic Affairs at the time and being much busier. I was a naive young faculty member at the time. I'd inherited the course that you and Nan had been teaching, which was a course really quite different, and I actually thought it was quite bold of you to teach a course on what were relatively modern, recently developed methods of longitudinal analysis, not primarily targeted at our doctoral students, but really at a much broader audience of graduate students across all of the departments of the School of Public Health. I suspect when you developed that course, there wasn't a course like that in any other biostat department in the country.
Probably.
And I don't know if you have any memories of the first year or two you taught it. I would have had trepidation taking on such an endeavor, but you boldly went ahead with it. And so I was wondering if you could maybe just, because I don't know the history of the course, what motivated it?
So I have some memories, very fond of that course, but actually I believe that our advanced multivariate course, I had taught that for a while, and that itself had changed a lot.
Yeah, right.
And we'd sort of ended up calling it modern multivariate, I think, to emphasize the fact that it wasn't just the traditional.
So you had moved away from that traditional statistics department multivariate course, that using all the traditional
methods,
I also
to
something that
was of very limited utility for our students.
The sorts of problems, exactly.
And then, so I don't really know exactly how the idea to teach a course that was aimed at the students in other departments, I don't know exactly how that evolved, but I believe that I taught it in the beginning. I don't really recall what the enrollment was, and I recall teaching it for a few years, though, and then I recall Jim and I taught it together for a year, and then Jim took it over and taught it for a couple of years. And so as I was saying earlier, one of the things I remember so clearly about that course was when Jim took it over, Jim used a lot of the teaching materials that I had developed in the previous year or so, as of course he would. And he would take a handout that everything pretty much was handwritten back then, because we didn't really have the level of word processing that we have now. And so it would be handwritten in my hand, and things would be pasted, and it was a cut and paste job. And Jim would white out my name and put a little tag over it and say, "Where?" and Jim and I had such different handwritings. I thought anybody can look at this and know that Jim Ware didn't write what's on this piece of paper. And it really got to me, though. At the end of the course, the students rated us both, and I remember several students commenting, "Well, Jim Ware is such a much better teacher than Professor Laird." So, in fact, even if you look at his handouts are so much clearer and better than Dr. Laird's handouts. That really got to me.
Jim, do you want to defend yourself here?
No, I, as in every other way, I do so much benefit from Nan's work. And of course, when you took over the course, I mean, I'm a great believer in sharing materials. I gave you everything I had.
Yeah, it was much easier at that time for me to change the name, because you'd kindly typed them up, and so they couldn't detect the differences between our handwriting. I just simply erased your name and put my name down.
And I think the first year you teach a course, that's so helpful, because there's so much to do. And then after that, you take it over and you really then shape it the way you want to. And then that course had a great run, and I think David Whippy had a period of teaching it also somewhere in that mix. But I think that course has had enrollments in excess of 100 some years. It's really been popular.
It's still being taught.
Yeah, I'm actually teaching it this semester.
Yeah, and it's again now part of the armamentarium of the clinical, of the research epidemiologist or clinical investigator who wants to have a toolkit of statistical methods.
Right.
So Garrett, what made you to decide to go ahead and write a book based on the course?
Well, I think it was a number of things. First of all, it was being young and naive. So I was a relatively young faculty member then. I think when I first arrived on the faculty, I took over the course from Jim, and after 2 or 3 years of teaching it, I believe, again, part of it was response to student evaluation. So at the time, we had a very well-developed set of course notes, but the students would always complain about the lack of another source. These were not doctoral students in biostatistics, and I think there was always this desire to be able to go to another source to get reinforcement of what they were learning in the classroom. So I think it was prompted in part by the students. It was prompted also by the fact that I was lucky enough to get a junior sabbatical. And so when Jim refers to the fact that, you know, the two of you had already had this idea of writing a book for many, many years, but never really got it off the ground, I think, you know, being freed up for 6 or 8 months to be able to just concentrate on writing was really what moved it forward. But I think the third factor was the fact that I was able to convince the two of you to be involved in it. I would never have undertaken such a project without your input, and I really, you know, it was an absolute capstone experience for me. I would say it's definitely the one piece of work that I feel very proud of. We spent a lot of time, we put a lot of thought and care into the work, and you know, I think it paid off. And I remember early discussions that we had about you know, some of the issues about trying to write a book to appeal to a broad audience, and also, you know, should we make it broader? You know, at one point, I think we thought about maybe writing a book to appeal beyond public health, and then I think we wisely decided to sort of stay where in the area we're familiar with, to use examples that would resonate with our intended audience, and I think that was kind of key. So I think that the impetus came probably from students. The decision to do it was probably a little bit naive, thinking that a well-developed set of course notes could just quickly be turned into a book, which is not the case. Requires really a lot more thought and care. That sort of involvement in the book also sort of had an important impact on my career, because one of the features of the book that I recognize that it really plays a role in translation. We've talked about the time lag between getting important statistical methodologies into implementable computer programs, but there's also been a lag in terms of the translation of useful and important statistical methods and their use in mainstream. And courses are one way that we try to sort of bridge that, but I think textbooks are another way. And so I'm sort of curious about, you've had many years of experience as sort of dedicated educators. Is there any lessons you've learned about what can really help to sort of quicken that translation? I don't think we've always done a great job. It's often taken a long time. I know, Jim, you've been particularly involved in the New England Journal of Medicine for 25 years, really, as a statistical editor. And during that time, I wonder, have you seen the impact of some of the methodologies we've been talking about in terms of the papers that are now being submitted to the journal?
I was a couple of times, I think in the 90s, I was asked to write a kind of historical perspective on the development of statistical methods. Once, I think it was Circulation that asked me to do it. And another time it was maybe one of the epi journals. And so I went back to the 80s and looked at statistical practices in both the clinical and the epidemiologic literature. And it was remarkable how limited they were. It was descriptive and t-tests, and maybe you'd see a linear regression somewhere. And that was it back in the 80s. And now if you read even a journal like New England Journal, which tries not to be too methodologically heavy because it has such a wide readership, but you see a lot of sophisticated statistical methodology now in both the epi and the clinical literature. And of course, fields like causal inference have just stretched our brains, really, really challenged us to think more deeply. And I would say in this particular area of analysis of longitudinal data, I think over the last, 5 to 7 years maybe, I've seen a real transition toward more common use of these more sophisticated methods. Not only the ones that Nan and I worked on back in the 80s, but I'm talking about things like, spline functions embedded in linear models and things like that, that people are really using these models now in much richer ways, and it's appearing in journals like New England Journal. So partly it's because of the tremendous interest now in research using these big databases, the so-called big data kind of phenomenon in terms of using, for example, the Scandinavian databases to do different kinds of studies that involve such massive data sets that it justifies more sophisticated methodology. But I think there's been no question now. You see these students that come into the clinical effectiveness program that are fellows at the Harvard hospitals, and some of them are quite amazing in how much they know and what aspirations do they have to become sophisticated data analysts.
Nan, do you have any suggestions for how we can sort of quicken the pace? Because Jim refers to the past 5 or 7 years, but yet we've probably been teaching these methods for many years. And the other thing I was just particularly struck by, again, remembering when I was a student, which is 25 years ago, is how little the way in which we teach many of these courses to particularly the non-biostat students, how little they've changed. And so I wonder, is there room for development in terms of the curriculum for many of these quantitative scientists?
Yeah, I think
that's possible. I guess, Garrett, the way I think about it is, in particular, what I think you have done is the textbook, and I give you 90% of the credit for writing the textbook, is so clear, it's so consistent, it's so careful in presentation of the material so that the audience can see immediately what's going on. And it's so full of examples. So I think, if you say much of the material in courses hasn't really changed, makes you wonder if people teaching the courses aren't engaged in research, because so many things have happened that really require that we have new methods, right? So just as I mentioned earlier, the fact that when you have chronic disease with clinical trials, it's no longer survival anymore. It's repeated measures, and that really required a different sort of way of analyzing the clinical trial data. And it's taken a long time, but and I think our work and your work has really helped that along. But also now when you think about it, there's so much genetic data that was never there before. And it requires a lot of new thinking about how to develop methods. I think an issue with genetic data is we aren't really there in terms of where we were in 1982 with methods for longitudinal data. We're just not there yet. And the sort of type of data and the availability of data changes rapidly. So you have to have a really good idea and a way of solving it. You have to be engaged in practical research and problems. And you have to be a really effective communicator. As you said, it's really hard to write a good textbook. And that's not something that is so valued in academia.
I think that's true.
Yeah.
It's really been fascinating to hear about the very pioneering and important work you've done as a collaboration. I know it's really gone beyond an academic collaboration. It's the two of you have had a sort of a deep personal friendship, and so I know you're both too modest to, if I asked you each to sort of summarize, really, some of your most important contributions, in particular to longitudinal data analysis. So instead, I'm going to ask you to sort of comment on what you've sort of gained from each other from your collaborations. So Nan, perhaps you could sort of talk first about Jim.
So, well, definitely one thing I've learned about collaborations is if you find someone you work well with, keep that person and do everything you can to continue those collaborations. But I would say one thing I learned quite early on when Jim first came to the school is although you do need to worry a little bit about working on the problems that you think you're supposed to be working on, if you see an opportunity, which in my case was the opportunity to work with Jim on the Six City study, even though I wasn't funded to work on the Six City study, if you have an opportunity that looks fun and interesting and exciting, take it. And I guess the third thing I learned from Jim was how important it is to keep your eye on the discrepancy between what's out there for people to use to analyze their data and the kinds of data that they actually have and what new methods can be developed.
So from my perspective, meeting Nan was the most important event in my professional life, I think, because it transformed my career. That when I met Nan, she had the insight, the creativity, the methodologic background to just bring my aspirations to fruition and to bring the quality of my work up to an entirely different level. And we had this wonderful laboratory of data that we could work with, and so that made all the difference for me, and it was just a blessing. And Nan and I, we had our bumps. I mean, I remember when I published a paper in American Statistician, and Nan said, well, this is our joint work. Why are you publishing it as your paper? And my answer was, I'm trying to get tenure, and which wasn't a very good answer, but that was my answer. But so it wasn't always harmonious. We had our disagreements, but darn few, boy, in all those years we worked together. And Nan, I feel blessed to have had you as a colleague all those years, and how much I learned from you. And last year, we had an event to celebrate Nan's career, and the students spoke about her in a way that I admired so much. What a great mentor you are, how skillfully and thoughtfully you guided students, and you brought those same skills to our relationship. So it's been wonderful.
Thank you, Jim. I would like to just add one thing. So, I'm sorry, this is breaking me up. People have often asked me, who was my mentor at the school? And we place such emphasis on mentoring junior faculty. And I always say, well, Jim Weir was my close colleague and my peer, but he was my mentor. He was the one who taught me everything I knew at the school.
Mm.
Well, I'd like to thank both of you for taking time to, really describe such important aspects of your career, your work with us, and really an amazing collaboration that, many of us would sort of wish we were so lucky to have.
Mm-hmm.
So thank you both.
Thank you, Garrett.
You're welcome, Garrett.